Welcome back. And I've shown you how to draw different isomers given a molecular formula. And the next reasonable step to take without making huge leaps would be to understand boiling point. It's a very, very simple concept. There are two underlying rules that govern how alkanes, at least, can behave in terms of boiling point. But if any of you don't know what boiling point really is, if someone asks you what is boiling point, you don't say things boil. Okay, that's more of an observation rather than an actual definition of what is boiling point or why something boils. So here I have a flask containing just water, and I'm heating the water. As water begins to go from liquid, okay, as it begins to go from liquid to gas, what you develop is something called vapor pressure. Okay, I'm going to write it. Vapor pressure. Over here, this area. And here is your atmosphere. Okay, this is the atmosphere in which you're heating your water or whatever you're heating in a room, kitchen, maybe a lab, surface, whatever. That's your atmospheric pressure. That has a certain pressure, and that's called atmospheric pressure. When the vapor pressure and atmospheric pressure equals out, that's when a liquid begins to boil. You see, equal means it has to be equal. Each liquid has a unique property which makes it boil at different temperature. Not all liquid boils the same temperature. Water boils at 100 degrees Celsius. Alkanes, well, different alkanes boil at different temperature, and we're trying to figure it out. So what I have done here is I've given you three different structures, and I think I have worked out a few structures in my previous videos for each of these three compounds. So I'm going to write the unbranched for each of this. So for C3, C5H12, I'm going to keep the colors the same. So, so that's the unbranched or straight chain or parent. There's a whole bunch of ways that it's called. I'm going to similarly write a unbranched or parent chain for C6H14. And similarly, I'm going to draw one more straight chain structure for C4H10. You see the colors match. This way I can actually make my point more clear. Now, I'm just going to pick one random structure. It doesn't have to be what I drew. It could be anything, okay? So this is where I think it makes sense to have if you remember, this was one of the structures. Similarly, I'm going to draw one branch structure. Now, I'm just picking the first structure. It doesn't have to be the same structure, okay? Now, if you see, this was one of the structures. This also has 6 carbons. This was one of them. Similarly, I also drew this one, right? If you remember, I've done this as well. So say I have the 6, okay, in a distillation flask, okay, like this flask right here. Let me pick actually a different color. You will see this, okay? This is a distillation setup, okay? This is a distillation flask, and you will distill and collect your, liquid one at a time in a beaker, okay? Here I have all 6 of them, okay? There's 6. How do I know what is coming out first, and how do I know what is coming out second, what is coming out third, 4, 5, and 6? They all separate at different times. There's 2 primary rules, okay? Higher the number of carbons, okay? Higher the boiling point. So That's the first rule. Don't jump in and start saying, oh, this will, this will. No. The second rule is more branching, okay, means lower boiling point. You got to apply both rules to actually determine which one would come out first, which one would come out last. So I'm going to give a completely different color to differentiate it. So let's pick this pink, okay? Okay, let's pick pink, all right? Actually, let me make the thickness much smaller. That's good enough, okay? So we have 6, right? And the higher the number of carbon atoms, higher the boiling point, right? So clearly, we have 2 6-carbon containing compounds, and one of them has to be the higher, but this has branching, this doesn't. So this would be the highest boiling point, which I'm going to give it number 6, okay? All right, and this would be next in line to it because it would still be higher, but it will be less than, it'd be higher than the 4 and the 5 carbons, but it would be lower than this because it's 6, but it's got branching because there's branching, so it's lower boiling point. All right, let's pick a green, and we'll change the thickness as well. And then 5, between these two, this would take the 4th spot, this would take the 3rd spot. Why? They both have 5 carbons, but one is branched, the other is not. And this would be, you know, out of this 2, this would be 2, and this would be 1. So 1 has the lowest boiling point, right? And 6 has the highest boiling point. And that is it. So if we're going to put all the 6 in that flask and distill, which one do you think will come out first? The one with the lowest boiling point would come out first. So 1 would come out first, followed by 2, followed by 3, followed by 4, 5, 6, and so on. So lowest boiling point distills first. Highest boiling point means this takes less time. High boiling point means it takes more time. And that's all there is to it in terms of branching and straight chain. This is only for alkanes. We can extend the same logic to alkenes and alkynes, which we will worry about it later. But for now, we're only interested in understanding boiling point of alkanes. Only saturated hydrocarbons, also known as alkanes. All right, so stay tuned for further videos.